Okay, let's pick up where we left off last time. We were talking about internal flow momentum concepts, and we got to the point where we were just starting to talk about some of the thermal concepts. We have a few slides left from last time. We'll go through, and then we'll, for the rest of today, talk about how you actually use correlations in internal flow. Again, this might be some stuff that if you've had heat transfer recently, 364, you probably remember some of this, but it's good to review it, and maybe you can see it again in a new way. All right, so last time, like I said, we started with this internal flow thermal concepts, and we were talking about how in internal or external flow, we have the boundary layer that develops over the plate. We're pretty familiar with that now. And of course, it remains external flow because the boundary layer never interferes with anything else. It just continues to grow as like a 1D transient conduction problem would grow. It just continues to grow over space until it eventually becomes either turbulent or the flow ends. All right, so the boundary layers, when they do meet, we get this fully developed flow, and that shows up in the heat transfer relationships as a sort of steady heat transfer coefficient or steady useful. Once it becomes fully developed at this point, in internal flow, the flow characteristics stop changing, as opposed to external flow where it continues to change. Okay, so that was kind of review, and then we went through and started drawing the temperature profiles as a function of position, where we said coming in, there's this uniform temperature here. As we're exposing the fluid to the heated surface at TS, that fluid will start to heat up, and we get this temperature gradient here that we're familiar with. In the middle region, it remains at T infinity until you get to the fully developed region, where then the entire profile looks like a parabolic shape. Yes. As you move, unlike the momentum boundary layer, which becomes, it stops developing, it stops changing after the fully developed one, the temperature profile can continue to change. And it can do it in basically one of two ways. So let's say we have, in this case, we have constant surface temperature. So the way the flow, the temperature profile continues to change is that it will converge to TS. Some infinitely long pipe, you're going to have perfectly uniform temperature flow across the entire process. The other way that it can continue to change is if you say had constant heat flux, the entire profile is going to continue to shift upward, and we'll talk about that a little later. But if you were to then plot the mean temperature of the fluid at any sort of slice in this direction as a function of position, you would see that for a fixed surface temperature, the mean temperature is going to approach it with something that kind of looks like an exponential curve. This kind of looks like a lump capacitance problem in a way. So we can write out the mean temperature. So the mean temperature is called the bulk temperature, or sometimes called the mixing cup. Don't ask me, I don't know why, mixing cup temperature. And that is, the equation for that is m dot times specific heat capacity of the fluid times the mean temperature is equal to rho times C times the area integral over the cross-sectional area of T times U times dAc. Okay, so that is the equation to get to the mean temperature. So one thing you'll notice is that inside that integral over here, right here, both temperature and velocity appear. So that's giving weight to whatever velocity is highest in the profile. That temperature at that velocity is given a higher weight in the overall mean temperature. So you can't just look straight across the profile, take the mean temperature of the profile, and get back the mean temperature. It actually does depend on the velocity. I guess that kind of makes sense because you have more mass moving through at a higher rate. That's going to correspond to kind of a more important part of the mean temperature calculation. So anyways, this is how you calculate the mean temperature for a flow like this. And if we wanted to write out the local heat transfer coefficient, we would do that So our heat transfer coefficient, we would do that in one of two ways. So, well, for internal flow, it's just one way. So internal flow, it would be our local heat transfer coefficient at some position x is equal to q dot double prime, the surface heat flux, divided by the temperature difference between the surface and the free stream, sorry, the mean temperature, right? This is, well, it's just the rate equation, but expressed for this problem. So the local heat transfer is the surface heat flux divided by the temperature difference that the fluid sees at any point along the flow. So at any point along the flow, it's not T infinity anymore. We're actually having driving temperature difference between the surface temperature to the mean temperature, which is changing as a function of position, right? And so that's for internal flow. For external, right? Just to compare, remember that was Hx is equal to u dot double prime over Ts minus T infinity. So our definition is slightly different for internal flow because we're thinking about what is the driving temperature difference at any position. Okay, so let's think a little bit about where the thermal boundary layer becomes fully developed. I know we kind of have this fully developed position, xFD. We calculated that for the momentum consideration. Let's do the same thing for the thermal consideration. So we do that, we have delta T, assuming this flow is laminar. So our thermal boundary layer thickness in the laminar region is given by 2 times the square root of alpha T, which is the same thing as 2 times the square root of alpha x over um, where is the mean velocity. Okay, so now if we know that the layers meet in the middle, that's a dh over 2, then that's going to give us 2 square root of alpha x fd t laminar. So that's the fully developed thermal boundary layer when it's laminar flow. That's that position divided by our mean velocity um. Okay, so then we can go through and solve for xfd. We do that, it's just algebra. You end up with xfd thermal in the laminar flow regime divided by d sub h is approximately equal to, let's see, d sub h over 16 times u sub m over alpha, solving that equation. To get this a little bit more useful for what we want, let's multiply by nu over nu, or kinematic viscosity. This times nu over nu, and then that's going to give us 1/16 dh um over nu times nu over alpha. Okay, so this here is the Prandtl number. And this here is, sorry, not the 1/16, just this is our Reynolds number in terms of dH. Okay, so we can rewrite this then with what you normally see, which is xfdt laminar is approximately equal to 0.063 times Reynolds in terms of dH times our Prandtl number. Okay. So no big surprise there. The thing that's maybe interesting is that you remember our xfd h laminar was just 0.063 times Reynolds. Now we have, the only difference here for the thermal is the Prandtl number. And again, that makes sense, right? Because when we're talking about growth of boundary layers, those things are related. They both start at the same position by the Prandtl number. So this is saying if I have a Prandtl number of greater than 1, my fully developed thermal layer is going to occur later than it would if it was looking at the momentum part of it, right? Said that a little backwards, but so your Prandtl number just scales how these fully developed positions actually occur. And if we look at a direct comparison of those two things, that is x fdt laminar that directly to XFD momentum, or I think we call it H laminar. That is just equal to Prandtl number. Yeah, Tyler.
What was the T in the complication?
Oh, sorry, up here.
Yeah.
Time. But yeah, we just convert the time to a position based on velocity. Yeah.
What happened to the DH on the left side of the equation?
Oh, which, yeah, still there. Thank you. I don't know why. I feel like every time I go through this, I forget that pH. So I should just put it on the bottom of the slides. Okay, so here, okay, so now we see a relationship between the thermal fully developed position and the momentum fully developed position. And that's saying that that's directly related to the Prandtl number. So again, it's just the rate of boundary layer growth. That's how they're related to each other. Don't get confused though, because remember Prandtl is also equal to, or it is equal to nu over alpha, which is a momentum divided by a thermal. Here, the boundary layers are the inverse of that. The fully developed positions are the inverse of that. It's thermal over momentum because we're talking about the growth, so the position of growth becomes the inverse. So that's pretty clear. So let's just quick sketch out what this might look like. So here, let's draw a duct. Okay, so we have our duct. So let's first think about a Prandtl number that is greater than 1. So if I have a Prandtl number that's greater than 1, and I draw, let's draw the momentum boundary layer, and that goes like this. So this is where this here is X, FD, H, or momentum, and so XFDH. That's where it becomes fully developed. The same thing I call it, yes, XFDH. So if the Prandtl number is greater than 1, then where are my thermal boundary layers going to meet? Is it going to be before or after XFDH? Yes, after. So it's going to look something like this. So this is going to be our XFDT. Because we are the momentum boundary layer in a Prandtl number greater than 1 is growing faster than the thermal boundary layer is growing. So they're going to meet sooner, and you're going to have fully developed velocity boundary layer faster than you would a fully developed thermal boundary. Okay, you can do the same thing for the other way around, but of course you can imagine it just flips. So I won't draw that one. Any questions on that? Okay, let's think about transition to turbulence here. Let's see, not leave myself an extra slide. That's okay, I think I can do it down in the corner. So let's think about the transition to turbulence and how that affects the growth of the thermal boundary layer. So let's say we have a situation, draw another duct down here in the corner. And in this duct, we have, let's say this occurring, we have the growth of a momentum boundary layer. And then at some point here, we have a transition to turbulence. The momentum boundary layer transitions to turbulent flow. So that's going to look something like this. The transition might go, okay, this, where it pretty quickly then becomes fully developed. And then we move on the full way, and it's fully developed turbulent flow. Okay, so this is our delta. So I guess we're using H. It's our momentum or velocity boundary layer. Going to pick a subscript there, right? Delta H, we'll call it, not thermal. So what happens if, let's say I have a thermal boundary layer that's growing, Prandtl number is greater than 1, my thermal boundary layer is going like this. Okay, so it's growing, but growing more slowly than the momentum boundary layers grow. So what happens when we transition to turbulence? How does the thermal boundary layer grow? Is it going to become fully developed later than the momentum boundary layer? Or what? Think about that. Yes, exactly. So what Ryder said is it's going to happen simultaneously because what are the mechanisms that are determining momentum transfer versus heat transfer in turbulent flow? They're the same mechanism. So whereas in the laminar flow region, we're governed by the molecular properties, in the turbulent flow region, we're governed by the eddy properties. And the eddy properties are commonly shared between the heat transfer and momentum aspects of the problem, right? So when you transition to turbulence, the stuff you had before that kind of goes out the window. They all are going to converge at the same time, the same fully developed position. So this here is our turbulence, and then we call this what, X crit for turbulence, and then this is going to be XFD for both thermal and XFD for momentum, both at the same position. Okay, and again, those happen really quickly after the critical length is reached.